Hey everyone, and welcome back to AI.Code.Cast. We're diving deep into more of those daily coding challenges that help us keep our problem-solving skills sharp.
Absolutely. It's like a daily workout for your brain, you know?
Exactly. And today we're tackling a problem called check if n and its double exist.
Well, this one's a good one. It
Uh,
really gets you thinking about efficiency.
right. Like, how do we find what we need in data without, making the computer work too hard?
And it pops up everywhere. Think about financial analysis. You need to see if a stock has doubled or halved.
Or even in game development, you might need to quickly check if a player's score is double their previous high score.
Yeah. The applications are endless.
Never.
So, we asked our community for their solutions, and wow, you guys did not disappoint.
We got some seriously impressive approaches, and that's what we're going to break down today.
We'll start with the brute force approach just to get a feel for the problem, and then we'll explore some more elegant solutions and see how they stack up against each other.
Sounds like a plan. So let's start with the basics. What exactly is this check if n and its double exist problem all about?
Okay, so imagine you're given an array of integers, which is basically just a list of whole numbers.
Okay, got it. An array of numbers.
Right, and the goal is to figure out if there are any two numbers in that array where one is exactly double the other.
So like if we had the array 10, 2, 5, 3, we'd see that 10 is double 5. So we'd say true. Right.
Exactly, you nailed it.
Awesome. But what if we had an array like 3, 1, 7, 11?
Well, in that case, there are no doubles, so we would return false.
Gotcha. So it's all about finding these double pairs. But is there anything else we need to keep in mind, like any tricky edge cases or rules?
Good question. There is one little catch. The two numbers in the pair have to be at different positions in the array. So no cheating by using the same number twice, even if it's its own
Well,
double.
that makes sense. So we can just say that 0 is its own double because it's in the array twice.
Exactly. Good catch. So now that we have the problem down, let's talk about the first approach, brute force.
Brute force. It sounds kind of well brute.
It does, doesn't it? But sometimes it's a good place to start. Basically, we just try every possible combination until we find what we're looking for. It's like searching for your keys by checking every single drawer and pocket.
Okay, so in our case, we would compare every number in the array to every other number.
Yep. We'd use nested loops to do that. Pick a number, compare it to all the others, and move on to the next one.
I can see how that would work, but it doesn't seem very efficient, especially if we have a really big array.
You're absolutely right. That's the downside of brute force. It can be really slow for large data sets. It's what we call O of n squared complexity. Basically, the time it takes increases exponentially as the array grows.
Oh, wow. Yeah, that sounds pretty inefficient. So brute force is simple to understand, but not the best when it comes to speed.
Exactly. But it's a good starting point to understand the problem before we move on to more clever solutions.
Okay, so brute force is off the table.
Hmm.
What other approaches should we explore?
Well, there's one that utilizes a really handy data structure called a set. You familiar with sets?
I've heard of them, but maybe you could give us a quick refresher on what they are and how they might be useful here.
Sure. A set is a collection of unique elements. Think of it like a bag that only allows one of each item. No duplicates allowed.
Okay, so how can we use this no duplicates rule to our advantage in this problem?
I'm going to let you think about that one for a moment.
Let me see. So we're looking for doubles and sets, only store unique values. Maybe as we go through the array. I think I've got it.
Go on, I'm all ears.
What if we add each number to the set as we encounter it? If we find a number that's already in the set, that means its double or half must be somewhere in the array.
Bingo. That's exactly it. You're a natural.
Wow, really? I'm starting to get the hang of this.
I can tell. So instead of comparing every number to every other number, we use the set as a super fast lookup table.
Oh, I see. We're treating a bit of space to store the set, but we're saving a ton of time.
Right on. And time is precious, especially when dealing with large data sets. So what do you think the time complexity is for this approach?
Well, we only have to go through the array once, right? So it should be much better than O of n squared.
You got it. This approach has a time complexity of O of n. That means the time it takes increases linearly with the size of the array.
Wow, that's a huge improvement. But what about space complexity? We are storing all those numbers in a set after all.
That's a great point. The space complexity is also O of n because in the worst case, we might end up storing all the numbers from the array in our set.
Okay, so it's a trade-off. We're using more memory, but we're saving a lot of time.
Exactly. It's all about finding the right balance for your specific needs. But hey, we're just getting started. There are even more clever approaches out there.
I'm intrigued. Tell me more.
Well, one approach combines the power of two classic algorithms, sorting and binary search.
Wait, sorting. How does sorting help us find doubles?
Ah, that's where the magic happens. Once we have a sorted array, we can use binary search to find the double of a number super efficiently. Remember how binary search works?
Yeah, it's like looking up a word in a dictionary. You keep having the search space until you find what you're looking for.
Right, and since our array is sorted, we know exactly where to look for the double of a number.
So we sort the array first, and then for each number we use binary search to see if its double is in there.
You got it. And this approach gives us a time complexity of, let me think, it's O of n log n.
O of n log n. That sounds pretty good. What about space complexity?
Well, that depends on the sorting algorithm we use, but it's generally better than the set approach. Many efficient sorting algorithms have a space complexity of O of log n, or O of n in the worst case.
Okay, so we've got brute force set lookup, and now sorting with binary search. They all have their own pros and cons. Are there any other approaches we could try?
There's one more I want to talk about. It uses a frequency hash map, and it's especially helpful when we're dealing with negative numbers.
A frequency hash map. That sounds interesting. Why are negative numbers a special case here?
Well, think about how sets work. They only care about unique values. But when we're talking about doubles, the sign of the number matters. For example, 2 and -2 are different values, but one is the double of the other.
Ah, I see. A set wouldn't be able to capture that relationship.
Exactly. And that's where the frequency hash map comes in. It's like a tally sheet where we keep track of how many times each number appears in the array.
Okay, so it's not just about whether a number exists, but how often it appears. But how does this help us find doubles?
Well, imagine this. Our hash map has keys, which are the unique numbers from our array, and values, which are the counts of how many times each number appears. So if we have the number 2 in our array 3 times, our hash map would have an entry like this: 2, 3.
Okay, I'm picturing it. So we build this hash map by going through the array and counting the occurrences of each number. Then what?
Then we go through the array again, and for each number we ask the hash map, hey, does the double of this number exist as a key? And if it does, we know we found a pair.
So we're essentially checking if for every number there's a corresponding double that's been tallied up in our map.
Yep.
What happens if we have a negative number?
That's the beauty of the hash map. It can handle negative keys without a problem. Unlike an array where we can't have negative indices, a hash map doesn't care about the sign of the number.
Right, that makes sense. So how does this hash map approach compare to our previous methods in terms of efficiency?
It's quite similar to the set lookup approach in terms of time complexity. We only need to loop through the array twice, once to build the hash map and once to check for doubles. So it has a time complexity of O of n, just like the set approach.
That's great. And what about space complexity?
Similar to sets, the space complexity for a frequency hash map is also O of n in the worst case. This is because, at most, we'll be storing a count for each unique number in our array.
Okay, so it sounds like the hash map approach offers similar performance to the set approach, but with the added bonus of handling negative numbers gracefully.
Exactly. And that wraps up our discussion of the different approaches to solve the check if n and its double exists problem. We covered brute force set lookup sorting with binary search and the frequency hash map.
Wow, that was a whirlwind tour of algorithms and data structures. It's amazing how one problem can have so many different solutions.
It really shows how important it is to understand the trade-offs between time complexity, space complexity, and the specific needs of your application.
Absolutely. Big thanks to you for breaking down these approaches with us. And to our listeners, we hope you enjoyed this deep dive.
Yeah. Keep practicing and exploring different algorithms. You'll be amazed at what you can achieve.
We'll see you in the next episode of AI.Code.Cast. Until then, happy coding, everyone.
Happy coding.
Okay, I think I'm good for now. So let's move on from brute force. What other solutions did you mention?
Well, there's one that uses a really neat data structure called a set. Are you familiar with sets?
I've heard of them, but maybe a quick refresher would be helpful.
Sure thing. A set is basically a collection of unique elements, kind of like a bag where you can only put one of each item. No duplicates allowed.
Okay, I get it. So no duplicates. How does that help us with this double problem?
I'm going to let you ponder that for a moment.
Let's see. We're looking for doubles and sets. Only store unique values. So maybe as we go through the array, we could... I think I've got it. What if we add each number to the set as we go? And if we encounter a number that's already in the set, that means we found its double or half earlier in the array.
You nailed it. You're a quick learner.
Awesome. So instead of comparing every number to every other number, we just use the set to check if we've seen a double or half before.
Exactly. We're basically trading a little bit of space to store the set for a huge gain in speed.
Right. It's like we're optimizing our search by remembering what we've already seen. So what would you say the time complexity is for this approach?
Well, with the set approach, we only need to go through the array once, so the time complexity drops down to O of n.
O of n. So much better than that O of n squared from before. But what about space complexity? Are we using more memory now that we're storing these numbers in a set?
Good point. You're right, the space complexity is also O of n because in the worst case, we might have to store every single number from the array in our set.
Okay, so there's always a trade-off. More space for less time. It's like a balancing act.
Exactly. It all depends on your priorities and the specific constraints of your problem. But the good news is we have even more options.
Oh, tell me more. I'm really enjoying this.
All right. This next one is a real head-scratcher. It combines two classic algorithms, sorting and binary search. Have you ever used binary search before?
Yeah, it's like looking up a word in a dictionary. You keep having the search space until you find what you're looking for.
Exactly. It's super efficient for searching sorted data. But how does sorting help us in this double finding quest?
I'm not sure I see the connection yet.
Well, think about it. If the array is sorted, we can use binary search to very quickly check if the double of a number exists.
Ah, I see. So we sort the array first, and then for each number we use binary search to see if we can find its double.
You got it. This approach gives us a time complexity of, let me see. It's O of n log n.
O of n and log n. That's still pretty good, right?
Definitely. Much better than brute force. And what about space complexity?
What's the space complexity for this approach?
The space complexity depends on the sorting algorithm we choose, but it's usually better than using a set. Most efficient sorting algorithms have a space complexity of O of log n or O of n at worst.
Okay, so we've got brute force set lookup, and now sorting with binary search, each one with its own set of trade-offs. Any other strategies up your sleeve?
I've got one more at my sleeve. This one uses what we call a frequency hash map, and it's especially handy when we have to deal with those tricky negative numbers. Remember how sets only care about unique values?
Yeah.
Well, with doubles, the sign of the number can be important. 2 and -2 are different values, but one is double the other.
Ah, that's right. Sets wouldn't be able to tell the difference.
Exactly. That's where the frequency hash map shines. It's like a tally sheet where we keep track of how many times each number shows up in the array.
Okay, so we're not just checking if a number exists, but how many times it appears. How does that help us find doubles?
Okay, picture this. Our hash map has keys, which are the unique numbers from our array, and values, which represent how many times each number appears. So if we have the number 2 in our array 3 times, our hash map entry would look like this, 2, 3.
Okay, I'm visualizing it. So we go through the array count, how many times we see each number, and store that in the hash map.
Yep.
What's next?
Once we have our trusty hash map, we take another stroll through the array. For each number, we ask the hash map, hey, does the double of this number exist as a key? If the answer is yes, we've struck gold. We've found a double pair.
So it's like we're cross-referencing each number with our tally sheet to see if its double has been counted. What if we run into a negative number? Does that mess things up?
Not at all. That's the beauty of hash maps. They can handle negative keys with no problem. Unlike arrays where you can't have negative indices, hash maps are cool with any number you throw at them.
Right, that makes sense. So how does this frequency hash map method compare to the others in terms of efficiency?
It's pretty similar to the set lookup approach in terms of time complexity. We only have to go through the array twice, once to build the hash map and once to check for doubles. That gives us a time complexity of O of n.
O of n. That's fantastic. And what about space complexity? Are we using a lot of memory with the hash map?
Similar to sets, the worst case space complexity for a frequency hash map is also O of n. We're essentially storing a count for every unique number in the array.
So it seems like the hash map approach is just as efficient as the set approach, but it can handle those negative numbers without breaking a sweat.
You got it. Choosing between a set and a hash map often boils down to whether you need to keep track of how many times each number appears. If you do the hash map as your go-to tool.
Okay, so just to recap, why do we need the frequency hash map when we have negative numbers? Why can't we just use the set approach?
Right. Well, with sets, we're only looking at unique values. But with doubles, the sign of the number matters. 2 and -2 are distinct values in a set. But one is the double of the other. The set wouldn't be able to recognize that connection.
Got it. So we need something that can handle those negative numbers without getting confused.
Yeah.
That's where the frequency hash map comes in, right?
Exactly. It's like a counter for each number. It
Okay.
tells us not only if a number exists, but also how many times it appears in the array.
Okay, so how does that help us find doubles?
Well, let's break it down. The hash map has keys, which are all of the unique numbers in our array.
Okay.
And for each key, we store a value, which is the count, how many times that number shows up.
So if we saw the number 2 3 times in the array,
Then our hash map would have an entry that says 2, 3.
2, 3. Got it. So first we go through the array, build up this hash map with all the counts, and then what?
Then we go back through the array, and for each number, we ask the hash map, hey, have you seen the double of this number before?
So we're checking if the double of a number exists as a key in our hash map.
Precisely. If it does, boom, we found a double pair.
And the hash map can handle negative keys without a problem, right?
Absolutely. That's the beauty of it. It doesn't care about the sign of the number. It just uses it as a key and stores the count.
Okay, I'm seeing the power of this approach. So in terms of efficiency,
Nice.
how does it compare to the other methods we've discussed?
It's very similar to the set lookup approach in terms of time complexity.
Right.
We only need to loop through the array twice, once to build the hash map and once to find the doubles. That gives us a time complexity of O of n.
O of n. That's amazing. And what about space complexity? Are we using more memory with this approach?
Just like sets the space complexity for a frequency hash map is also O of n in the worst case scenario.
Because we're storing a count for each unique number.
You got it.
Okay, so it sounds like the hash map approach is as efficient as the set approach, but with the added advantage of gracefully handling those negative numbers.
Exactly. Choosing between a set and a hash map really comes down to the specifics of your problem. If you need to track how many times each number appears, a hash map is definitely the way to go.
This deep dive has been incredible. We've gone from brute force to sets, to sorting with binary search, and now to frequency hash maps. It's fascinating how many ways there are to solve one problem.
It really highlights the beauty of algorithms and data structures. It's like having a toolbox full of different tools, each with its own strengths and weaknesses.
Absolutely. And by understanding the trade-offs, we can choose the best tool for the job. Big thanks to you for guiding us through these solutions.
It's been my pleasure. Always happy to talk about algorithms.
And to all our listeners out there, keep practicing and exploring new approaches to problem solving. The more you learn, the more fun coding becomes.
Absolutely. Don't be afraid to experiment and try different things.
We'll see you in the next episode of AI.Code.Cast. Until then, happy coding, everyone.
Happy coding!